Agentic AI refers to artificial intelligence systems that behave like goal-driven agents rather than simple response machines. Instead of producing a single output and stopping, these systems think in steps. They decide what to do next, take action, observe results, and adjust their approach. An agentic system can continue working toward a goal even when conditions change. This makes agentic AI suitable for complex tasks that require reasoning, planning, and adaptation over time. Agentic AI should be used when a problem requires multiple steps, decision-making, uncertainty handling, or continuous improvement. Examples include research assistants, project planning systems, monitoring systems, and autonomous task managers. These problems benefit from agents that can decide what information is missing, choose actions, and revise strategies. If a task is simple, repetitive, or requires a single response, agentic systems may be unnecessary and inefficient. Agentic AI is not always the best solution. If a task is straightforward, deterministic, or requires strict control, a simple rule-based system or single response model is often better. For example, formatting text, translating a sentence, or answering a factual question does not require planning or autonomy. Using agents in such cases increases cost, complexity, and risk without adding value. Agentic AI systems are built using modular building blocks that work together. These include goals, memory, reasoning, tools, feedback loops, and control mechanisms. Each block has a clear responsibility. Goals define what success looks like. Memory stores experience. Reasoning determines decisions. Tools extend capabilities. Feedback evaluates outcomes. Control mechanisms ensure safe and aligned behavior. Removing or weakening any block reduces the effectiveness of the agent. Building blocks can be categorized into decision blocks, memory blocks, execution blocks, and evaluation blocks. Decision blocks determine what to do next. Memory blocks store context and history. Execution blocks perform actions such as searching or interacting with systems. Evaluation blocks assess whether actions were successful. Well-designed agents balance all block types to behave intelligently rather than impulsively. Workflows define how an agent organizes its steps to achieve a goal. Unlike rigid pipelines, agentic workflows are flexible. They adapt based on outcomes and feedback. Workflows allow agents to break complex goals into manageable phases, decide execution order, and revisit steps when needed. Choosing the right workflow structure is critical for efficiency and reliability. Prompt chaining is a workflow where the output of one step becomes the input for the next step. Each step focuses on a smaller part of the problem. This approach improves clarity and accuracy for complex tasks such as analysis, summarization, or planning. For example, an agent may first outline a report, then expand sections, then review clarity. Routing workflows allow an agent to choose different paths based on input or context. Instead of following a fixed sequence, the agent decides which action or specialist to use. For example, a customer support agent may route technical issues to one process and billing issues to another. Routing improves efficiency and relevance. Parallelization workflows allow agents to perform multiple tasks simultaneously. This is useful when tasks are independent and can be completed faster together. For example, an agent may gather information from multiple sources at the same time before combining results. Parallelization reduces latency and improves throughput. In this workflow, an orchestrator agent manages the overall goal while worker agents handle specific subtasks. The orchestrator assigns work, collects results, and decides next steps. For example, a project management system may use one agent to plan and several agents to execute research, writing, and validation tasks. Evaluator optimizer workflow is separate creation from evaluation. One component produces results, while another evaluates quality and suggests improvements. This loop continues until the output meets standards. For example, an agent may generate a draft while another agent reviews clarity and accuracy. This structure significantly improves reliability. Agents can be categorized by role. Task agents focus on execution. Planner agents focus on strategy. Evaluator agents assess quality. Coordinator agents manage other agents. Memory agents handle context and history. Real-world systems often combine multiple agent types to achieve complex goals efficiently. Frameworks provide reusable patterns for building agentic systems. They help manage memory, workflows, tool usage, and agent communication. Frameworks are useful when building complex systems with many agents or workflows. However, for simple use cases, frameworks may add unnecessary complexity. The key is to adopt frameworks only when scale, coordination, or reuse becomes important. Agents rely on clear instructions when using tools. Prompt engineering for tools involves clearly defining what the tool does, when to use it, what input it expects, and what output it returns. Well-designed tool prompts reduce errors and improve reliability. For example, an agent using a search tool should know what kind of information to request and how to interpret results. Agentic AI represents a major shift from reactive artificial intelligence to autonomous, goal-driven systems. Understanding when to use agents, how workflows shape behavior, how building blocks interact, and how agents collaborate is essential for modern artificial intelligence development. As these systems become more common, the ability to design them thoughtfully will become a critical skill. If this video helped you build a strong foundation in Agentic AI, support the channel by liking, sharing, and subscribing for more deep, easy to understand artificial intelligence content.